In this video, we are going to discuss pipelining. Well, what is pipelining? In short, when we try to run several processes together or simultaneously, that's pipelining. Well, running several processes, one can think that there is a multiprocessor environment, so that's why we can run several processes together. Well, at times the infrastructure of a multiprocessor environment is quite costly, um, because more than one processor is a bit costly. So the solution is pipelining. If you have done Java, there's something known as threading. If not, don't worry, I shall discuss pipelining here. This pipelining concept is somewhat related to threading. If you know threading concept, this pipelining becomes easier to understand. The what happens in pipelining is, while one process is getting executed, um, at times the process has to wait for some time. While it is waiting, another process can begin. As a whole does not happen, the process gets divided first into a few sub processes, and then the suppose the process once sub process is executing, sub process 1 is executing, and then it has to wait for some time. At that stage, process 2 sub process may start. So let's see what's written here. Pipelining means when we are able to run several processes simultaneously in a uniprocessor system. In this case, we divide the sub-operation into k number of segments, and when a process executing segment 2, another process may be executing segment 1. What this means is, as you can see it's written here, in a uniprocessor system, so there is only one processor. In this case, we divide the sub-operation into k number of segments, saying that we divide an operation into segments. How many segments? K segments. K may be 3, K may be 4, K may be 5. We divide the operation in 5 segments. We divide the operation in K segments. The subdivisions, that is. In a process executing segment 2, and the process may be executing would be in segment 1. That is the first operations, segment 2 is getting executed, while the second operations, first segment is getting executed. In a non-pipelining architecture, if n processes running with k segments, it requires n into k number of clock periods to complete the task. What this means is, suppose one task, it has k number of segments. One task is divided into k segments. Let me first discuss what a segment means. Suppose this is an instruction, and as you know, in instruction there are few stages. First is opcode fetch, then opcode decode, then operand fetch, then execution, then write buffer. These are the 5 stages in which an operation each operation or instruction is broken down. So these 5 are the 5 segments. So k in this case is 5. So it's saying here, uh, if one process having k segments takes n clock periods, we're talking about non-pipeline architecture, means in which pipelining has not been implemented. In the non-pipelining architecture, if one process takes n clock periods, then uh, oh sorry, in a non-pipelined architecture, if n processes running with k segments, and suppose once time to execute one segment is n, so total time would be k into n, because there are n processes and k segments, so k into n number of clock periods. But in the case of pipelined architecture, it requires only k plus n plus one number of clock periods to complete the execution. This is k plus n plus 1. I shall discuss later why it is this way. Okay, this is a better picture. See, for one instruction, it has k number of segments. This segment takes one clock period. This takes another. This takes another. This takes another. This takes another. So k clock periods. One instruction takes k clock periods. If there are n instructions, it would be it would be k plus k plus k plus k up to n. That is n times k. So that's why in a non-pipelined architecture, it takes n into k clock periods. But in case of a pipelined architecture, what happens is the system operates in this way actually. Uh, in the first clock cycle, in the suppose this is the clock cycle and this is the operations. In the first clock period, process once opcode fetch is done. Okay, in the second clock period, process once opcode decode is done, and process 2's opcode fetch is done. In the third clock period, process 1's operand fetch is done. As you can see, process 1 operand fetch is done, and process 2's opcode decode is done. In the fourth clock period, process 1's execution is done, and process 2's opcode fetch is done. Process 2's opcode fetch is done. In the next clock period, process 1's write buffer is done, process 2's execution is done. So in this way, in the clock periods, as you can see, while the second segment of process 1 is getting executed, the first segment of process 2 is getting executed. So it happens sort of simultaneously. The job gets broken down and pieces of the job happen simultaneously. So this gives the effect of multitasking. So this is the concept of pipelining. Now let's move on to some of the technical details. A few terms we have to study actually: the speed up, then maximum speed up, then a few more. So let's begin. Speed up. What is speed up? Speed up of a pipelined architecture is the ratio between time to execute n processes in a non-pipelined architecture versus time to execute n processes in a pipelined architecture. In a k-staged pipelining, if the speed up is sk, so the speed up is denoted by s subscript k. The sk is, what is it, is the ratio between time to execute n process in a non-pipelined architecture versus time to execute n process in a pipelined architecture. So in non-pipeline architecture, the numerator versus the pipeline architecture is the denominator. Numerator, denominator. Non-pipelines What is speed up? The time taken to execute n number of instructions in a non-pipelined architecture versus the total time taken to execute n instructions in a pipeline architecture. This is speed up. What's the gain in speed? What's the gain in speed over the initial speed that we were getting? So speed up is nk divided by k plus n plus 1. Why is this? Why is nk? Because as I discussed earlier, look at this picture. In non-pipelined architecture, one instruction takes k clock periods. So if there are n instructions, it would take n into k clock periods. There are two instructions shown here. So k clock period plus k clock period, that's 2 into k clock period. Here n is 2, that's why 2k. If we take number of instructions as n, so there would be n into k clock periods. Versus in a pipeline architecture, as you can see, process 1 takes 1 2 3 4 5. Process 1 takes 5 clock periods. The entire operation gets over at 6 clock periods. That is 1. Oh, I'm so sorry, this is k plus n minus 1. K plus n minus 1, not plus 1. Sorry of this illegible handwriting. I'm sorry of this. These are not my notes. I've got it from someone, and I didn't really have time to write this myself. That's why this is minus 1, actually not plus 1. This is minus 1. K plus n minus 1. How did I realize this? As you can see, process 1 takes k clock periods, right? Here k is 5. It is 5 clock periods. Process 1, 5 clock period. And process 2 gets over at k plus 1 clock periods. So if you follow the formula here, it's k plus n plus 1, which is said, which is not true, just said. So n plus 1 means how many? N is 2. N plus 1 means 3. So it would have been k plus 3, but it's not that, it's k plus 1. So it's n minus 1. N is 2, n minus 1 means 2 minus 1 is 1. This is k plus 1 clock periods. So it's k plus 1. So formula is k plus n minus 1. So let's plug it here. Nk divided by k plus n minus 1. That is speed up. Now observe this formula. Nk divided by k plus n minus 1. When can we have the maximum speed up? When will sk be maximum? Sk, okay, observe the denominator. K plus n minus 1. K is fixed, okay, n number of instructions is a variable, and minus 1 is a constant. So in the denominator, and the variable is n, the numerator as well. So we can change the number of instructions only. If you observe carefully, so our target is to obtain maximum speed up. We have to make certain adjustments so that we can maximize sk. Let's see how. As the number of tasks increases, n becomes very large. It becomes much larger than k plus k minus 1. So n is much greater than k. So k plus n minus 1 is almost equal to n, because k is 5 and n is 10,000. So 10,000 plus 5 is 10,005, which is almost equal to 10,000. So this is k plus n minus 1. So nk divided by n, which gives k. So speed up is k. That is, the maximum speed up in a linear pipelining can be achieved is k, where k is the number of stages of pipeline. Well, you can raise a point here. If the number, if the speed up is k, then if we increase the number of steps, if we keep increasing the number of steps, then we can have a better speed up. Well, this is not true. I won't state the reason right now, but just note that if we increase the number of stages to more than 5, there are certain problems. So the optimum level is 4 to 5. That is the optimum. The number of stages is 4 to 5. Efficiency. Efficiency of a linear pipeline is measured by the ratio of busy time space over total time space. Busy time space plus ideal time space is the total time space. Let's see. If n is the number of tasks, k is the number of stages, and tau is the clock period, then pipelining efficiency is defined by eta. Eta is the efficiency. Eta equal to n k tau by k into k tau plus n minus 1 tau. I'm pretty sure you understood anything. Okay, so what is tau? Tau is the clock period. Okay, n into k is the number of clock periods, and tau is the time, the exact time to, means what is the clock period. N into k is the number of clock periods, right? And tau is the numerical value of it. Suppose I'm saying there are 5 clock periods and one clock period is over 100 nanoseconds, so 5 clock period means 500 nanoseconds. So total time in a non-pipeline architecture is n into k into tau. Now pipeline architecture is k plus n minus 1. This is total thing, so total into tau. So we cancel out tau, tau cancels here, here, then what's remaining is actually all wrong things written here. I'm so sorry. Suppose this, look at here, the number of instructions, the number of instructions is k plus n minus 1. Okay, so this is the total number of clock periods, and one clock period takes tau amount of time, so this total into tau would give the total time taken. So k tau plus n minus 1 tau is the total time taken. So the efficiency is n k tau divided by k tau plus n minus 1 tau. If we cancel out tau, what's remaining is n divided by k plus n minus 1. Again the same argument, when n is much more than 1, when n is much more than k, then k plus n minus 1 is almost equal to n, so n by n, which gives 1. So maximum speed up is 1, and this happens when number of instructions is much more. This is written here. This implies larger the number of operations through the pipeline, better is the efficiency. Throughput is very important. Throughput, number of tasks completed per unit time is called throughput. Is very, very important. Throughput is the number of tasks completed per unit. So time required to complete n tasks is equal to k plus n minus 1 tau. Throughput W is n by k plus n minus 1 tau. When n tends to infinity, k plus n minus 1 almost equal to n. So tau, so throughput, it's omega equal to 1 by tau. Again, 1 by tau is frequency, 1 by time period is frequency. You know that. 1 by time period is frequency. So it's throughput of linear pipelining. Okay, classification of pipelining processor. Pipelining is divided into 3 types: arithmetic pipeline, instruction pipeline and processor pipeline. What is arithmetic pipeline? Arithmetic The arithmetic logic unit of a computer can be segmentized for pipelining. The the ALU operations can be segmented into pipeline. This example given here, star 100 is one of the examples. This is something. This is not uh, something that I should teach you so that you can understand. It's pretty much you have to read through them once. Just reading. Instruction pipeline. The execution of a stream of instruction can be pipelined by overlapping execution of current whatever uh, instruction pipeline. That is this one which we are talking here. This is the instruction. The instructions are coming. We are pipelining it here. Instruction pipeline. Then processor pipeline. Some data stream passes through a basket of processor feature which is a specific task. Data stream passes the first processor with results stored in a memory block accessible to second processor, and then refined result passes to third IO. Okay, this we shall discuss later. For the time being, just read through all of them. Definitions may come. This is all for this video, nothing new. We are not completed pipelining actually. There is much more left, even to the extent that we are discussing scalar pipelining. Then there is vector pipelining, array processor, and a lot of things are left actually. But if we continue further, this video will become too long. So let's stop it here. If you like this, do share it with your friends. Thank you.